Now we're going to quantify the concepts of equilibria, which we learned in the last section. We're going to quantify that by actually looking at the actual numbers, okay? So recall that the symbol, boom, is placed between reaction and products, and we use that when we're talking about reversible reactions, or reactions that go in equilibrium, okay? Now, since they're reversible, we can quantify that by saying we can take the products, the amount of the products, and we can divide by the reactants, and that'll give us a ratio, right? And that ratio we're going to call Q. All right, that's the reaction quotient. The reaction quotient allows us to mathematically express the amounts of reactants and products present at any point in a reversible reaction. All right, so for example, let's look at this reaction. Consider the general reaction A plus B produces C plus D, where A, this little a means A moles. A moles of A plus B moles of B produces C moles of C plus D moles of D, okay? So they're either gases or aqueous species. And when we do this, we say, when we use the amounts, when using amounts expressed in concentration, the reaction quotient is called QC if it's concentration. So we're going to say QC. So QC is the products over the reactants. Now this is an important feature here. We are going to raise the amount of products to the power of the moles there, okay? In other words, just look. We're going to memorize that. This is like saying C, the concentration of C times the concentration of D. And if there are two C's, then we're going to say it's C squared times D. And if there are 2 moles of D, we're going to say C squared times D squared, right? Divided by that. All right? So it's the products over reactants, and we're going to raise them to the powers of the molar coefficients. All right? Now, concentrations need to be expressed in terms of molarities, right? Because it doesn't make sense if they're not. It turns out this symbol or this ratio is defined by molarities, all right? Product concentrations are in the numerator, the reactants are in the denominator, and each concentration is raised to the power of its coefficient from the balanced equation. So it has to be balanced. All right, so the value, the numeric value of QC for a given reaction, it varies prior to equilibrium. So we found in a previous conversation, let me go back up and show that, right? Remember this? We were looking at this, and we said if the amount of N2O4 is going down, and this is the reactant, right? Here's the reactant right here. And so remember, in this conversation, Q is equal to the products over reactants, right? Products over reactants. And so the reactant's actually going down. That means this number is getting smaller. That means Q is actually getting bigger, right? When the denominator gets smaller, the ratio gets bigger. So Q is changing over time. Where was I here? The numeric value of Q for a given reaction, it changes until we get to equilibrium. Once we get to equilibrium, then the value doesn't change. The value of QC doesn't change anymore. The value of QC depends on the concentration of products and reactants present at any particular moment, okay? Now we can calculate QC at any point in the reaction so long as we know what the concentrations are. We oftentimes calculate QC at the start of the reaction, and we use the initial concentrations, and we say QC at the beginning, and we use the initial concentration, right? So in this example, we might say if we have a reaction where there is 0 C or D, in other words, we don't have any of this stuff yet, then QC, these are going to be 0 up here, right? And so QC is going to be 0. Can you see that? As the reaction proceeds, the value of QC increases because the products increase, right? And the products are in the numerator. All right, so given enough time, any reaction is going to eventually reach equilibrium. And at equilibrium, the relative amounts of products and reactants no longer change, and therefore the value of QC no longer changes at equilibrium, right? I've got a figure for that, and here it is. And we're going to call Q at that point, we're going to call it K. That is, when it reaches equilibrium, Here's the reaction quotient, right? The reaction quotient, it starts out at 0 because you have 0 products, and it goes up, right? In the shape of a curve we're going to call sigmoidal. Won't use that term a whole lot, I guess, but it goes up until it reaches equilibrium. And when it reaches equilibrium, it doesn't change anymore. At that point, QC is defined as K. All right? And so we would say it is at equilibrium when QC is equal to K. Okay? Let's go practice this stuff.